Uh, okay, I think it has started, and so let's let's get started with the discussion. So I think just like last time, I wanted to start with and perhaps have a slightly extensive discussion on the Queen DDoS problem that was discussed, I think, in the very first week of the course. But there are a few things regarding linear algebra and some vector calculus. So I thought we'll do that along with problem solving today. Okay. So yeah, welcome to week 4. This is optimization from fundamentals. So last time we could not cover problems or ideas corresponding to the lecture 6C, and that is about so the question is want to solve. By the way, I just want to confirm, you can hear me and you can see me, right? Can you just confirm the window once?
Yes.
Okay, all right. So what we want to do is we want to solve Ax equals to b, but the problem is, problem or rather the situation is that A is a fat matrix, meaning it's an m cross n matrix where m is less than n. Okay, and at most you can have rank to be m. Say it is m. Still, null space is not trivial. Okay, this means there are infinite possible solutions. So whenever I solve Ax equals to b, there are so many solutions possible. So what do I do? How do I go about picking it? Right. So we will look for only certain types of x. Okay. Sorry. I want to solve this and infinite possibilities. So we will look for only certain types of x. Okay, and one way to do that would be to find the least norm solution. So this is nothing but saying find the vector of the smallest length, and the constraint is that of course it solves the system of equation. Okay, I think someone has joined. Okay, hi Soumyadeep.
Hi.
Yeah, so I mean just started, so let me briefly recap. So last time we could not cover portions from lecture C, so I'm just quickly going through what we trying to do in this lecture C, which is about minimum norm solution for linear system of equations. Okay, so the problem that we are given is you have to solve x equals to b, and it's a fat matrix, meaning the number of rows are fewer than the number of columns, fewer equations and more number of variables. and so because of this, the null space of this matrix A is not going to be trivial, and hence there are a lot of solutions possible. So if there is a solution X for A, then you can always have AX plus A applied to X plus B, A operated on X plus B, X plus Z, which will give B, because Z is in the null space of A, and I can multiply the Z by any scalar, and hence I can have infinite possible solutions. So which one to pick, because I want to solve the system. One way to go about it would be to formulate it as saying, okay, I want a solution which of course solves the system of linear system of equations, but at the same time also have the least length. Okay, so that's what we want to do. So just as an application of what we have learned, so our Lagrangian, so here there is only one constraint, or actually okay, sorry about that, let me okay, hold on. Are you able to still see my screen?
Yeah, it's visible.
Oh, okay, sorry, I'm not sure what happened. Anyway, so yeah, let me just so yeah, what I'm saying is here, can you correct me if I'm wrong? Is there only one constraint here?
No.
Okay, so how many constraints are there? So let's say A is m cross n. Let's say A is m cross n. So how many constraints will be there? I'm not asking about the number of variables, I'm asking how many constraints will be there.
So if A means n cross n, there should be one constant, right?
So so maybe let me write it down. So this Ax equals to B is nothing but m equality constraints in conjunction, right? Ai transpose x equals to Bi, where I is starting ranging from 1 to m. So I'm just stacking it in a matrix and then writing it compactly in this matrix vector product, right? Does that make sense?
Okay. So okay, yeah, got it.
So that means I have m constraints. So I'll just compactly write it as this lambda transpose Ax minus B.
So lambda should be a m-dimensional vector, right?
Yes. So that means lambda will be some m-dimensional vector. Okay. So when you apply the first order necessary condition here, which we saw last time, which is that the gradient of this should be 0. So when we apply this, what we end up getting is x is A transpose lambda by 2. Okay. So maybe let me write x star, because we are looking for an optimal solution. So this is our candidate optimal point. Also notice that I have to satisfy the constraint Ax star equals to B, because after all it has to solve the linear system of equations. So if I put this value that I got by solving this gradient of the Laplacian equals 0, if I solve that system of equations, I get x star in terms of this lambda. So actually here let me put both x star and lambda star, because I am looking for a candidate solution, right? So what we'll end up getting is A transpose lambda equals to 2B. So lambda star, so this implies lambda star is simply A transpose inverse 2 P, and when I put it back ultimately in X star, what I'll get is X star is A transpose inverse P. So it's okay, this has been done in the lecture, that's fine, but I there's a reason why I'm doing this, because I want to ask whether this one crucial step is clear or not, and with that I want to then digress a bit into some linear algebra basics, cover that, and then come back to problems. So my question is this, my question is, we have written this, no, A transpose whole thing inverse in two places. So we assume that this A transpose is invertible. Why is that? So question, A is fat matrix, so M is less than N. A is full row rank.
Yeah, full row rank. Yeah.
Let's say it is given, okay, full row rank.
So it will be M cross M, right? A transpose.
Yeah, so A transpose is M cross M. So Y is A transpose invertible, meaning Y is rank of A transpose M. What's the proof? Any thoughts?
So full, if it's full row rank, that means it should have M pivots, right?
It should have M
pivots, means
correct. Yes.
So yeah, so by that we can reason the determinant is not equal to 0. So for A, at least for A, we can apply that reasoning. Yeah,
no, you can't even compute the determinant. Its determinant is only for square matrices. This is a rectangular matrix.
Yeah. True. No, I am asking for A transpose. So right. For that I can calculate, right?
No, but how will you calculate that? I am not giving you a specific A, right? If I give you A, you can numerically check this, but I'm not giving you all that I've given is this analytical setting where I'm saying that for any A which is a full row rank matrix, which happens to be this fat matrix, if I use that A to construct this new matrix A transpose, that is invertible. That's a square matrix. It's an invertible matrix. So how to prove that? Any thoughts? So one way to go about it is this. So for questions like this, typically can at least start with deriving some expressions based on the matrix form that you are seeing here. For example, you are seeing A transpose on the right side. So let's just see what happens if I say that. So this is a digression, by the way. Okay, we are answering this question through this D2. So let's say A transpose X is 0. Then by definition, X is in null space of A transpose, right? This is just a definition. Now, here, if I pre-multiply by the matrix A, so on this vector, if I multiply by A, so first of all, that is a valid operation, right? Because this is M cross M, this is M cross 1. Or, N cross M and M cross 1, and so hence you will get M cross N into N cross 1, so it's a valid operation. So you have A transpose X, on the right side is 0. So what have we gotten? So we have gotten that if X is in the null space of A transpose, then X is also in the null space of A transpose. So which means every element of null space of A transpose is an element in the null space of A transpose. Let's look at the other side. A transpose is X. So what we are given belongs to the null space of A transpose. Okay. So what can we say from here?
We can transpose this equation.
We can transpose this. So that will give X transpose A transpose. Okay.
Yeah, that doesn't do anything because it says X is the row space of, yeah, doesn't help.
So maybe some other observation. So okay, how about this? So this is a vector, right? This, let's call it y. A is 0. What can you say about y?
So Y is a null space of A, right?
Correct. So let me just skip one small step. Y is basically A transpose X. It's in the null space of A, right? Anything else that we can say? What can we say from here? So what do we want to prove? Let's just take a look at that. So roughly speaking, if we can establish something about my null space, if I can establish it to be for this A transpose matrix to be equal to null space of A transpose, then I'm sorted out because I already know this information. So by rank nullity theorem, I can simply say that then null space of A transpose is going to be trivial, because of which I can say that rank of A transpose is M, and hence I can say A transpose is invertible. So that's where we are headed. So whatever we showed here, we just want to show the other side. We want to show that any element of A transpose, null space of A transpose, that lies in the null space of A transpose. So we started from here. A transpose X is 0. So basically we are saying X is an element in the null space of A transpose, and from here we want to say that this element actually is in the null space of A transpose. So how do we do that? So one obvious thing, like you pointed out, is that from here, if I say A transpose X is 0, I can say that okay, this A transpose X, that itself lies in the null space of A. But beyond that, can we say anything?
Means we have to prove that X lies in the null space of A transpose, right?
Yeah. So how to do that?
Can we by any chance apply the transpose to both sides and come up with some conclusions? Just thinking. It's just
You mean to say here?
no. The last step means the last line which you have written
Here,
means
here.
yeah, because a transpose is already there. I'm thinking if you can some. I'm not sure. I'm not sure. It's yeah, this linear algebra thing. I'm mostly so.
Okay. Okay. So can I just do one thing? Can I just maybe ask you people to try it out? If you don't get it, it is just one more step in between. That's all. Just from here, we need to show that x. So how to do that? Just want you people to try it out because it will be important.
Yeah, you leave it at that. I'll just want to try out. Yeah, don't give away the last step.
Yeah. So ultimately, this will show us this null space of A transpose is null space of A transpose. So will be 0, and hence because A transpose, when you take n cross m, so the null space is going to be what? 0, right? Because it's going to be full column rank. Transpose of A. Transpose of A will be full column rank, right? So it's going to have 0 trivial null space. So that's why we can say that rank of A transpose is M. Okay. So I thought we could just quickly take a look at that. So what we will now do is we'll just
Deep, I have a small question.
yes.
So, when we apply the pseudo inverse, is it doing the same thing as forming a least norm solution
Pseudo inverse for what exactly?
for inverting a system of equations when there means when the null space is A is not empty, means not does not have the trivial solution. We have a way of inverting a matrix like that, right? Which
Yes.
doesn't have a true inverse.
Yes.
So by doing that pseudo inverse thing, are we approaching the same solution as optimizing here? What we did?
Let me think. So when you say pseudo inverse, as far as I understand, you are just saying that this thing is a pseudo inverse, right? You are just defining
Yeah,
this thing to
yeah,
be a
yeah,
pseudo
yeah.
inverse,
True.
right?
So is it the Moore-Penrose pseudo inverse? This is the one.
I think so. I just check it as sorry, I don't remember the name, but if I understand correctly, when we are solving this type of system of equations, and we end up arriving at these results, and then we call that okay. Instead of an inverse, we get some other kind of transformation, and let's call that as a pseudo inverse. Like ideally, I would want it to be A inverse B, but actually I can't because I have my constraints from the way I've obtained the data. I think this is what it
Yeah, I
needs to
think
be
it is.
written.
Yeah,
Yeah,
I think it is. Yeah, maybe that is the same. Yeah, that is the same
yeah.
inverse.
Anyway, I'll just check it out and I'll get back to you later. Okay. Uh, so yeah, I'm just deliberately leaving this out. Okay, just one or two steps here. Please try this out. Okay, it's not so difficult.
Yeah, it's a good teaser, a good exercise in the evening.
Okay. Okay. All right. So you can also maybe try showing contrapositive or something like that. And anyway, just give it a shot so that you can get some practice. So I just want to use that as an excuse to. Oh, maybe before that, let me just quickly go through the assignment 3 problems that were remaining. We couldn't do. Assignment 3 remaining questions. I couldn't do it last time. There were some 4-5 questions. So these are all mostly straightforward. So right now I'm looking at question 5. So I have to solve Ax equals to B again, m cross n, m less than n. Rank of A is m, full row rank. So what can be said about the solution of x? 0, 1, infinite. Any thoughts?
It should be infinite.
Yeah. Okay. We have another similar looking problem. Ax minus b squared. Again, this is m cross n, but this time m is tall. Matrix is tall, so m is greater than n. So what you will end up having instead of A transpose, you can similarly prove, by the way, A transpose A is invertible. So just like we showed here, for a full row rank you have A transpose as invertible. Similarly, you here have A transpose A as invertible. It's exactly the same proof, it's just a transpose. Transpose is invertible. Okay, that's what we are given. Full column rank. Full column rank is what we are given. Okay, so in this case, is the minimizer unique or not? So okay, so what do I need to first of all say? So x star, what would it look like? Can I solve for this analytically?
It may not be always solvable, right?
So I have given some crucial piece of information, which is that A transpose A is invertible. So we are given that A transpose A is invertible, meaning that A is full column rank. So note that is a tall matrix, it's not a fat matrix. So the difference here is, if you notice here, I just said okay, you minimize this. So I forgot to write minimize, but you minimize x over x such that this square is minimized. It's slightly different from here in the sense that here I want to solve the system exactly. The question we are looking at right now, it's okay if we are if we are close enough to ax equal, close enough in the sense that ax is very close to b. Find an x such that here I want it to be exactly satisfied such that there is some constraint such that this norm x is minimized. Here I am doing something slightly different. So see, the reason why I am saying this is, let's look at the Lagrangian. Okay, it's an unconstrained optimization. I don't need to do that. It's just the same as writing. It's an unconstrained optimization case. So let me directly take the gradient of this and equate it to 0. What will it be? So you have x transpose so what are you given? Ax minus b transpose ax minus b. How would you take the gradient of this? So just if you're not familiar, just check this out. You can take partial derivatives and verify this. Treat this as a single term, so it's x square, so just 2x. The 2 gets cancelled with this term here. Okay, and what's remaining is, treat this as now a function of x. You take the derivative of just this term, which happens to be a transpose. Just match the dimensions appropriately. This is what you'll get. This is a standard vector calculus step. So what you will end up getting is A transpose Ax equals to A transpose B. So what can we say from here about x? Does an x exist? Is it unique? Infinite number of x, or what happens?
Yeah, this is x is unique, right? Because A transpose is important.
Yeah. So now you see, right, why the assumption is coming. Oh, sorry. A transpose. So there is this distinction, and even later on you will see in practice, often for example, when you are trying to solve, it is not there in the lectures, I'm just making a few side comments. So lot of times what we want to do is we want to solve this system of linear equations, Ax equals to b. Okay, so the thing is, it's difficult to solve linear systems equation. So maybe some small expressions that we can write on a piece of paper, we can solve it analytically, but if I want a computer to do it, it's not that easy. So a lot of times, and you'll see uh, some algorithms to solve it, we'll be using this as a running example. So what I want to do is I want to solve the system of linear equations, but I can keep some tolerance. Like I want Ax to be as close to b as possible. I want to find such an x. So that's where we end up minimizing this type of a problem. So it is prevalent in this sense. When I want to, lot of times when you see that if I'm trying to solve a linear system of equations, I will pose it as this quadratic optimization problem. It's a quadratic term, right? Order 2 term in x. So I end up posing the problem for this linear system as this quadratic problem and then solve this to find my x, which is an approximate solution for x equals to b. Okay, so this is also called regression. So you might be familiar with that name perhaps. And here, I mean, you can just think about it. The rationale here is that I will take more observations than the number of variables that I have, meaning it's a tall matrix. So as to then ensure I can solve this equation. So for example, this solution that I got, it requires me to have m greater than n, meaning number of observations of data observations that I have are more than the number of variables at hand. Okay, and the next question is leading right to the point where you can ask, okay, but what if A is bad, that in spite of having A transpose A, I mean, the rank is still not full column rank. So what do I do in that case? Meaning A transpose A need not be invertible. So you can do what's called regularized least squares. So I'm jumping a bit ahead. It's question 8. So what you can do is, so this A transpose A. So let me not write this long version. Let me just write that rank of A need not be n. Okay, so in this case what we do is we want to add something to this matrix here so that it becomes full rank, and then take an inverse of that full rank matrix. Okay, so the one way to do it would be to optimize a slightly modified objective function. So what you can do is you can again minimize the same term, but you add something which is in your control. So you add this term which controls how big or small your solution is. So you minimize this instead.
So this is a reach objective, right?
Yes. So doing the same calculations, doing the same steps yields my x star to be A transpose A plus lambda I, the whole thing inverse. So what we have done is so originally we had this term A transpose A. Yeah, so originally we had this term A transpose A, but unfortunately that was not invertible. So what we have ended up doing is we added this term to improve the quote unquote improve the conditioning of the matrix. So we are biasing these entries so that overall, if at all there are any non-zero zero eigenvalues, then they become non-zero, and we can hence invert the matrix. Okay, so I posed it as a question, but then I didn't really solve it. I just gave the solution, but just wanted to point out that lot of times in practice it is this kind of least squares problem that we want to solve, because even solving linear system of equation is hard often. So we pose it as a different type of optimization. Well, it's good because you will soon see later. It's called a convex optimization problem. It has its own benefits. So when you pose it like this, we can get nice solutions. So different ways of finding solutions for systems of linear equations. Okay, and this is one way where we can ensure even when we have some non-invertibility issues, we can still find a solution for this system of linear equations. Okay. There is one question which is pretty straightforward actually. I just skipped that, but let me briefly mention it. If the B is A transpose A, A is M cross N, and it's also a tall matrix. B plus lambda I. So lambda is 0. Is this positive semi-definite, positive definite, negative semi-definite, negative definite, indefinite? Can we say anything about it? So again, just we'll apply the definition of what we mean. So if we take any vector x, and what we do is we take this type of inner product, weighted inner product. So this just gives us A transpose AX plus lambda IX, which is nothing but norm AX squared plus lambda norm X squared. Clearly this is greater than 0 for all x not 0. So we have our answer is this is positive definite, right? So this was the question. So let's move on to the question 9. So they have given quadratic function into variables x squared plus y squared. Take fxy equals to 1, which means the unit circle. And the question is, can we represent this unit circle as the graph of a function of just one variable? For a given set of variables, for given y and x. Can we do that?
It shouldn't be possible, right?
Can you explain why you think that?
Yeah. I just reasoned out because of the implicit function theorem, which
Yeah,
tells
correct.
us,
That's true. Yeah, that's true.
yeah, there should be a local neighborhood, right? Before
Yes,
we do that.
yes, you are right. So if I have x in anything between -1 to 1, then y is plus minus 1 minus x square. So I can't represent it as a graph of a single function. So like you said, implicit function. But in simpler terms, if I just solve this, if I try to represent y in terms of x, this is the problem I get, right? Which one to pick? So both possibilities are there. I can't use a single graph single functions graph to represent this unit circle. There's an optimization problem over two variables, and function is just the product of the two variables, subject to a line constraint. So can we rewrite this problem in something else? Can you simplify the problem? Maybe it's two variables. I don't want to solve into two variables.
Yeah, it can be written, right? You can just substitute one variable for the other, right, from the constraint.
And here, why can I do that? It's a line, right? It's implicit function
Yeah.
theorem, easily applicable.
Yes.
So I can just rewrite this as, say, 10y 10. Can just put x as 10 minus 3y into y. That's it. It's an unconstrained optimization problem now.
So a little correction. This is question number 10, right?
Oh, 10, yeah, sorry. Okay, 11 is not really a question, it's more like a comment. So, just for the sake of completeness, I state it. So, Lagrange multipliers, one way to think of it would be, so let's just take a simple case where you are minimizing f of x such that h of x equals to 0, and one of the constraint qualifications, which is what it's formally called, was that the gradient of f at the optimal point is a linear combination of the gradients of the constraint. So here, since it's only a single constraint, what we assumed for our theorems is that gradient f of x star plus lambda star gradient h of x star equal to 0. Or I can just write equal to. The sign doesn't really matter. I can just absorb it in the lambda star accordingly. So I have something like this. So here, based on that, the interpretation that the instructor gave is that this Lagrange multiplier lambda star, just take the ratio. Just think of this lambda star as a ratio of these two gradients. So first of all, what to say? Just a second. Right. So just think of this lambda star as a ratio of these quantities, and in a way it's saying that, like he put in the lecture, lambda star is basically saying that how much your optimal value changes when you change your constraint by a bit. So it's just trying to make that point, and to draw that analogy. Okay, so it's not really a question. So you can just.
So is this sensitivity analysis really helpful in practice? Because
Not that I know of. At least
yeah.
to be honest, I did not notice that this analogy before. Only after the lecture I realized that, okay, nice way to
Yeah,
maybe
I
think
also
of
didn't
it.
see that anywhere. Yeah, that's why I was asking.
Yeah, I'm not sure. I have not seen personally. So just final question before we move on to the week 4 questions. What is the difference between? So I did allude to this a bit. I was making these comments about solving some linear systems of equation. So A here is fat matrix and full row rank. So if I have a Yeah, let's just go through the options one by one. Not even contrast. No need to contrast with anything. So there are four options. This is a least squares regression problem. So these are the questions. Is it a least squares regression problem? It finds least norm solution to Ax equals to b, the system of equations. Problem may be infeasible. Depending on what a and b are, what a and b are. Problem has unique solution. So any thoughts, like which one is correct, which one is wrong?
For me, I had means already selected the first option, so I got this question as incorrect. And means I am not sure why. Means I thought that maybe it's also something akin to least squares regression problem only. I'm not sure why the answer is incorrect. Yeah, it's a least norm solution definitely.
Yeah, correct. So you are right about that. B is just stating in English what we want to do, right? What we have written on the left. It's the same thing. What about C, C and D? We'll come to A later, but what about C and D? So remember, I'm finding a minimum norm solution to this system of linear equations Ax equals to B, where A is a full row rank fat matrix. So what to say?
Yeah, so that is yeah, as you already pointed out, C is always possible to find the optimal point, right? Because of the full because
Correct. Yes.
so
So
C should be true. C shouldn't.
be
Okay,
true.
okay.
Yeah. C shouldn't be true. Correct. Because I'm
Yeah,
talking about
yeah, yeah,
infeasibility. Yeah.
yeah. Infeasibility. Yeah, that is.
And what about the last point?
Yeah, since there is an optimal point,
Correct. But uniqueness?
we can. Yeah, uniqueness. It should be unique, right? Means a least norm. Only one possible least norm should be there, right?
No, no. But how to say that? So that's what we feel, and it's correct. But so we need to appeal to this result, right? We saw in the lecture A transpose is invertible, so X star is
Yeah, yeah.
unique. Okay, so I have a full row rank assumption. I can get the closed form solution. So uh, we have already seen this, so it's just an application of the same result. So yeah, problem has a unique solution, and unique solution is exactly A transpose inverse B. Okay, but so right. So this is, I don't know. I mean, it's more like a convention and how. So regressing. I mean, you're comparing two terms, right? So that's the idea. So if you have, like I was saying, this is the problem. Where is it? A right. This one. This problem you can see here at question 6, where I'm
Yeah, yeah.
finding, finding minimizing the error between Ax and B by finding an appropriate X. This is called a least squares regression problem, because I'm minimizing the norm squared of the error, and the basically I'm trying to find an X such that Ax is close to B. So this would be termed as a least squares regression problem. So my laptop battery is low. Just give me a second. I'll plug in the charger. Meanwhile, if you have any questions.
You just mentioned something regarding constraint qualification. So
Yeah.
probably we'll come to those parts later, right?
No. So sorry. One constant qualification you already know, right? So for example, uh, I had written it somewhere. Where is it? Oh, I think I erased it. Okay, sorry. Yeah, let me just quickly write that down. So, constraint qualifications. So we saw that when we defined the Lagrangian, we said something like this: gradient at fx star is a linear combination of so let's say there are k constraints, and let's say these constraints are called fj's. So do you remember this condition that we used?
Yeah. I know.
Yeah, so this is called a constraint qualification. So one of the things I would require for when I'm defining my constraints is something like this, because we saw, right, with the way we want to define feasible directions, we would it would be nice, not nice, I mean, one way to realize that okay, I've reached an optimal point would be to say that the gradient at that point is a linear combination of the gradient of the constraints.
Okay.
Does that make sense, or should I explain again maybe?
Yeah, maybe a little bit more. I did not quite get it.
Okay, so what I'm trying to say is, you remember this case where we were looking for okay, let me write down on a fresh page. So what I'm saying is we had looked at this tangent plane, right? Can you help me write down the definition of tangent plane at a point, let's say x star?
Yeah, it's all those directions where D transpose yes means yeah D trans.
So this
Yeah.
won't be tangent plane, right? It will be feasible directions.
Okay, okay. These are the feasible directions. The tangent plane is formed by taking linear combinations, right?
Yeah. So let's just talk about feasible directions at a point x star. So this is something that I cannot avoid, right? If fj's are all the constraints, if I have to equality constraints, we just talked about equality constraints so far. So we will assume that there is some fjx equals to 0 for j equals to 1 to k. There are some k equality constraints. I have to satisfy that. So if I have to be on that surface fj for each j, that means the only way I can move is orthogonal to this gradient direction, right?
Yeah, yeah, yeah. True.
So if I say that, let's say at this optimal point, where is it? Just pointer, yeah, pointer is here. Okay, so I'm saying, let's say if I have reached this XR, which happens to be a maxima minima, whatever you call it. For in the class, the instructor has talked about it being a maxima, but it doesn't matter. So if it's a maxima, let's say XR is a local maxima. So then what is this condition trying to capture? What I'm saying is, if I am along the directions, some, as basically with my gradient direction, meaning the direction in which I can go to increase my function value, if it can be written as a linear combination of these gradients of constraints, that means I cannot move anywhere else to increase my function value. Does that make sense? I can only move orthogonal to that direction.
Okay, okay, okay. Yeah. Okay.
Okay, so
Yeah,
that is
yeah.
one way of realizing my characterizing, okay, what happens at when I reach the point that happens to be a local maximum. So that's why
Okay.
I say I require, let's say I put this as a condition when I say that, let's say I have reached a local maxima. If I have this condition, when gradient of the optimization objective can be written as a linear combination of the gradient of the constraints, then I can say, then because I have feasible directions defined like this for the equality constraints, I can say that okay, I indeed cannot move anywhere else, which makes sense,
Okay.
right?
Okay.
So that I
So
just,
this is a constraint qualification, right? How
yeah,
we achieve at the optimal point, right?
yeah. So these things I think he will probably cover later. So these things, this is one way of doing it, but you can define it in slightly different ways also. These are called constraint qualifications. I think it will probably come towards the middle or the end of the course.
Any book covers it apart from the Zach book? Has it the Zach?
Chong and
And
Zach. Uh, I think Chong and Zach, and there's another book by Nosidal. I think that book will also have some comments, some notes on this.
okay, I want to read it up. So later, yeah,
Yeah, sure.
I'll do it.
Yeah. Okay. I have about 1 hour. Okay, so what I will do is through the week 4 questions, if there are any doubts about the concepts, we'll do that, and then I have some linear algebra revision questions. So I want to go through that. So if at all at any point of time you feel that I am going fast or if you're not getting anything, please stop me. Okay. It's not like I have to cover each and every point, but I would like to cover both these things. So week 4 questions. So before we begin, briefly, if you have any questions about the definitions, can you please let me know so that you can clarify that before we move on to the questions. Any questions? By the way, you were asking last time about relative interior, so I hope that this week it's clear now. Now that he's defined it, why we, I mean, he gave more or less a similar example as to what I gave. So hopefully that
Yeah,
makes
yeah,
sense.
yeah. It's clear now. It's clear.
Yeah, but I did make one mistake in my definition though. So it shouldn't be ball intersection with the set itself. It should be the affine hull of the set with which I'm taking the intersection of the balls. There's
Yeah, yeah, correct.
one mistake. It's very important. Sorry about that.
Yeah, that affine thing should be there. It's that's that
Yeah, I
intersection.
need that subspace. So that's very important.
I got question three incorrect. This is convex set. I selected true. Means I have a doubt obviously for that.
Just so hold on. Any questions about the definitions? So I think there are
And,
two people, right? Yeah. So do you people have any questions in the definitions? Any questions about the material? Or I
so
can
I do
just
not
jump
have
in.
any doubts about any definitions as such.
Okay.
For
Okay.
me.
So I think then we'll just move on to the questions. Let's just go one by one. We'll come to. You have a doubt in question 3, right? Just come to it. Let's just look at it in a sequence. So if I have z to the 4, e to the minus 6z, and I am maximizing for positive numbers, okay, and call it some f star z star. So what is z star? So how do you people solve this? I mean, how did you people go about solving this?
I did it by plain old school calculus only.
So you just took the derivative of this function,
Yeah,
right?
yeah.
Yeah. So just to, you know, a brief call, a callback to the things that were discussed in the lectures. So what you can do is you can transform this problem into something simpler safely. So if you can, so we saw that one of the ways of transforming the problem, optimization problem, to still solve the equivalent problem is, let's say we have a monotonically increasing function. It's a maximization problem, so let me pick a monotonically increasing function. I'll just take a log. So what I'll do is I'll take log of f of z. So not that it's going to give you a different answer, it's just that it makes calculations a bit easier and also provides an example that oftentimes, here it's okay, it's a relatively straightforward expression, but oftentimes it would make a lot of sense to transform the problem to something else which is a bit easier to solve for. So if I take log of this becomes very straightforward. Now it's just 4 log z minus 6z, and if I do same, it's an unconstrained it's not an unconstrained optimization problem, but let's just derivative anyway you take 0 because Okay, yeah, let me ask this. So why is this still true? Why should I still do this? Here this will be a good revision. So why do I, how can I say that the condition d by dz, the derivative is 0 is still true? Because it's not an unconstrained optimization problem.
Yeah, it's an open set, right?
Yeah, correct. Right. So it's an open set, that's why I can do it. Right. So even though these things may seem trivial, but the more complicated the set gets, the more important it becomes to make sure to reason out these things. So z greater than 0 is open, hence the stated FONC for first order necessary condition.
So the idea behind this question is just to apply the transformations, right?
Yes.
I couldn't get the idea, so
Yeah.
I got it.
Yeah. The idea was to simplify it and then appeal to the fact that because this is increasing,
Yeah.
monotone increasing, so the both problems are equivalent in terms of solutions. Okay, except for if you want to find that optimal point, you might have to optimal value, you might have to just apply that lock. But other than that, the z star that you find here is going to be the same. So that's why you will get 4 by z minus 6 is 0, and hence z star is 2 by 3. So this was the point of the question. Okay, any questions? Okay, so same z star for maximizing fz as well. Okay,
So do we need to check for the whether it's a maxima or a minima by the sufficiency conditions is necessary?
I didn't get you. What is it?
No, means this may be a maximum or a minimum, right? So this is a necessary conditions you have checked, right? Those
Correct. Right. Yeah, you are right. I need to definitely do that. So I skipped that.
sufficiency.
So here it should be the derivative of this will be minus 4 by z square.
Yeah, so it's trivial, but yeah, I got that.
Yeah, correct. You are right. I should not skip that step. It's just the first order. Even if I, let's say, get if I get an expression which is just saying non-negative, even that won't cut it. It will just say that yeah, it's a candidate point, but I can't say for sure.
Yeah.
But here we are getting a strictly non-zero value, strictly non-negative value,
Yeah.
so it's fine. So this is the T2 phi z by dz. Okay, this is less than 0, so it's fine. Okay, there are 2 points given to us in the next question. X1 is 1 comma 2, there's another point 4 comma 7. So if I were to ask what is the convex combination of these 2 points, so this one doesn't really, it's not really conceptual. Just apply the definition of convex combination, and what you end up getting is 4 minus 3 alpha by, sorry, not by, this is the vector. So 4 minus 3 alpha, and we have 7 minus 5 alpha. And obviously alpha is between 0 and 1. So you just substitute different alpha values and you just compare with the options. So I think the correct answer is 39. I think there are 2 possibilities. 39 10 43 6 is one possibility, and another possibility is 19 by 5 and 20 by 3, these two vectors. So it's just an algebraic calculation. Okay, coming to the question that you had doubt in. So you have convex or not. Yeah, so you had some doubt, you were asking something, so you can discuss now.
Yeah, I had originally selected it as convex, so it's incorrect.
So let's just draw it, right? So this looks like a relatively simpler set. Let's just draw it. So you have 1, you have -1. So what will be S here?
So so it will be the union of two open boundaries, right? Open
It's
lines.
greater than equal to. So
Oh, okay,
basically,
okay. It's belong to R
yes.
or R.
So if I pick any point, let's say here and here, if I join this, it's not in S, right?
Ah, okay, okay.
So it's not convex. Does that make sense?
Yeah, yeah. I thought the set is a circle. That's why I was reasoning from there on. Means
Okay,
my
okay, okay,
bad.
okay.
My bad.
Yeah, that's the constraint. It's not the.
Yeah, yeah.
Okay, so this was not proved or discussed. I mean, he just briefly alluded to. But if you have C1 C2 as convex, then C1 intersection C2 is also convex, right? That's what was discussed in the class. What is the proof? How would you go about proving it?
Means I would say that since take any point of C1 intersection C2, so it must be in C1 and C2 both, right? Means at
Correct.
least C1, say. So
Yes.
C1 is already convex, so any convex combination should lie.
Yes. So yeah. So I'm just writing it down whatever you said. If you have X and Y which are belonging to the intersection of the two sets, that means they belong to the two sets. That means since they are convex, since they are convex sets, each of them, each pick any alpha between 0 and 1. So alpha x plus 1 minus alpha y, it will be in C1 and it will be in C2. This implies for x plus 1 minus alpha y belongs to C1 intersection C2 for all alpha in 0 and 1. This implies
Deep,
C1 intersection C2 is convex. So this
deep,
is true
Deep,
for,
I have a small doubt.
yeah.
So this is just a side point. So I was reading, if I remember correctly, I was reading for Boyd one's convex optimization, and there he said that any countably infinite collection of intersection is also convex. So
Okay, yeah.
in that case, how you should go about proving that any countably infinite?
Uh, yeah, so whenever these infinite intersections unions come there, you'll have to assume the axiom of choice.
Oh, the Zorn's lemma, right?
Yeah, so after that you can do it.
Okay. So we have to have used the axiom of choice, right?
Yeah,
In those cases.
I think so, yeah.
Okay. Okay.
Okay, so let's take another example, and again we will check for convexity. So if we have x1 x2 in R2, it's a line. So is is S convex or not?
for my own, I reasoned that it should be convex, but it came out incorrect. So
Okay.
my reasoning was it's a line or it's an hyperbola.
No, no, it's just x1 plus x2 equals to 5.
Okay, okay. Oh, this is 5, right? I was thinking about 6. Okay,
Ah,
okay.
okay. Sorry. Yeah, this is fifth. Yes.
5 is fine. Yeah, 5
Yeah,
is
it's
fine.
just a straight line, right? So
Yeah, that is fine.
this is convex. Right, this is convex. It's just a line. So coming to the question that you were talking about, S. So it's not just equality. There's also an inequality constraint. Inequality. So it's hyperbola
Oh,
and something beyond that,
yeah,
right?
yeah. I
Not
was
all the
thinking the
surface.
region outside the hyperbola, including the shell.
Correct. Yes. Yes. Outside and including the x1 x2 equals to 1. So let's just go back to this example. It's in the similar spirit. So here we had s equals to mod x greater than equal to 1, all such points, right? So the boundary was this. Anything outside this boundary, I mean outside this wall, was included, right? So then there is this gap. So if I pick any points and try to join a line, it goes through this gap. So it's not convex. A similar thing happening here. Instead of a erected wall like this, I have a wall like this, or other
So these are
one by
disconnected
x.
sets basically.
Yes, so it's one is going like this, another
Okay,
one is going like this. So hence, if I pick any point here and here, I can just again breach the wall,
got it. Got it.
right? So
But if it been a circle, it should be a connected set, right? Then it would be convex, right? Outside a
uh,
circle, all the region outside a unit circle.
correct. Yes, yes. So by the way, just to be, I'm although I'm skipping this, but it's very important. So when we say that it's not convex, we need to give an example. Okay, so so let's take 2 comma 2, 1 comma 1 will not work, I think, or maybe it will work, I'm not sure. 2 comma 2 surely works. So if you have 2 2, take the point on the other end. Yeah, I think 1 comma 1, any point with the same coordinates will work basically. Take alpha equals to 1 by 2. So call this x, call this y. Alpha x plus 1 minus alpha y is 0 0, correct? This does not belong to S. So whenever I say something is not convex, I need to give a counter example. When I say something is convex, I need to be able to prove that for any given point, the convex combination lies in that set. So for example, here, although I did not do in this case of in this question 5, but you have to take 2 points. So you take points a1 a2, you take points b1 b2, you take a convex combination of these, and you show that the whatever resultant point you get, that also satisfies this equation. I mean, it's obvious, it's just a linear equation. It will be ultimately the components will add up to 5, but what I'm saying is when you say that something is convex or non-convex, either you prove it or you give a counter example. Okay. There is another question. Here we have some kind of here we have a half plane. Half space, sorry, not plane, half space. So is it cone, half space, hyperplane, something else maybe? So any thoughts?
This is just a definition, right?
Uh,
Yeah.
Correct.
So,
Yeah,
half
it's
space.
just a definition. Nothing else to it. But half space is okay. But can we say for sure if first of all, is half space a cone?
Half space is, sorry?
Is it a cone?
No, it's not a cone, right?
Yeah, so it's not a cone simply because you can't extend in the other side, right?
Yes.
But that is for affine planes, right? I mean, why for cones? Cones should be okay, right?
No, cone should also pass through the origin, right?
Right. But here,
Here it is not passing through the
yeah,
origin.
exactly. Yeah. So I just wanted to go through the definitions. So obviously not a hyperplane because not an inequality. Uh, okay, there is one really obvious one which is S is a cone, and they are asking does the origin belong to S or not. So you just answered it. Yes, it does. There are multiple options here. So there are a few sets which are given and we want to see which of them are polyhedron. Mm, okay, yeah. C. So this is 1, 2, 3.
So, polyhedron is defined as an intersection of a finite number of half planes, right?
Half spaces, yeah.
Half spaces. So, it should be finite, right? We cannot take countably infinite.
No, finite number. It will be a finite number. Okay, so what about first one? So what are the characteristics of a polyhedron? Is it a convex set?
It should be. It is convex, yeah.
So in that case, can these two disjoint interval union of these two
No.
disjoint intervals, can it be a half? No, right? Because I can take the point, let's say 2 here and 3 here. Can take this point 2 and 3 and then take a convex combination of this. This won't lie in this set, right? This cannot be a half polyhedron because polyhedrons by definition are intersections of half spaces. Half spaces are convex. So this is non-convex. So this cannot be a polyhedron. So this is gone. Second option. What about this 1 to infinity?
So here we are talking in R1, right?
Yes.
So a plane will be R1 is just a point, right?
So we are talking about polyhedron here, not just planes. Half spaces, not
No,
just
I
hyperplanes.
no means half spaces should be defined by different sides of an hyperplane. I was thinking like that. So how do you define half spaces in one dimension?
So half space in one dimension will be just saying that's what. So anything, let's say x less than equal to a, x greater than equal to a. You put a equals to let's say 1.
So that's
So in a one dimensional case, this is true, right? It's basically polyhedron here is
Yeah, this is
equal to saying intersection of only one half space, which is the half space itself. No intersection. There's no intersection. I mean, it's just one half space present. Similarly, this one also, right? Because I can just take a half space which is x greater than or equal to 0. I can take another half space which is x less than or equal to 5. Can take an intersection of that. So this also makes sense, right? So if I'm on the number line, if I am 0, if I am at 5, I take this greater than or equal to 0. I take less than or equal to 5. So the intersection is what? Polyhedron, right? Is it fine?
yeah, it's fine.
Okay. And what about this? Let's say if you take any subset of this set, and it could be any arbitrary subset of this.
Yeah, this I had doubt. I mean, I did it incorrect.
Right. So what do
So
you think?
if it's a
So we already solved it, by the way. Just now we solved it a few moments ago. So
okay,
this
disconnected set. Yeah,
yes,
got
yeah,
got.
this is a subset of 0 to 5, right? So this is not true. Any arbitrary set cannot be a polyhedron. So, okay, so there are only two correct answers here. Okay, question 10. Alright. S is collection of a bunch of points in R2. 0, 0, 3, 0, 0, 2, 3, 2. So the question is, which of the following are in the convex hull of S? And the options are 0, 4, 1, 1, 3, 1, 4, 4. What do people think? Let's just think geometrically. What does it mean? We have 0, 0, 3, 0, 0, 2, 3, 2. So which points will lie within this filled rectangle? B and C, right?
Yeah.
So even otherwise you can see, you can just take the appropriate combination for that. Even there you can see the same. The next question is, you have a identity matrix, identity transformation, and we are looking at the following set all the vectors such that A times x less than equal to b. So what is this set equal to here? So by the way, the question is S a polytope or not? So polytope means it's a bounded polyhedron. So polyhedron is basically like you draw a bunch of lines, you take the intersection. So this is the polyhedron, right? But a lot of times what may end up happening is, so you may just get something like this, an intersection which is just unbounded. This is not a polytope. It's a polyhedron, but it's not bounded, so it's not polytope. So the one that I drew before, that was a polytope, which is because it's bounded. So that's the definition. So what do you people think?
This is false, right?
Why do you say that?
Because so I just drew the equations here, which are represented by this set.
Yeah.
So, so one is less than equal to 0. Sorry. Yeah. It's one half space completely. Right?
So it's this, right? Basically third quadrant.
Yeah. Sorry. Yeah. The third quadrant.
So it is
That is
unbounded.
unbounded.
So not polytope.
But this is a cone, right?
This is a cone, yes. Correct. So it's basically you have this and this third quadrant, this whole thing. That's our set. So it's a cone, yes. So I think this is the last question from the assignment, and then we'll move on to some linear algebra revision. So we are looking at the vectors where the first component is in R2 where the first component is non-negative, and similarly we are looking at a set B where the second component is non-negative. And C consists of a set of vectors where the first component is less than equal to 1. Similarly, D is same thing but for the second component. So there are a few things we need to try out and verify whether they are true or not. Is A a half space? Is A intersection B a polyhedron? Is A intersection C a polytope? And A intersection B intersection C intersection D is a polytope. So which of these are? Let me create a duplicate of this. Okay, and let me okay, so just give me a second. Something wrong with the application. Okay, yeah. So yeah, anyway, this is a question. So we are given these again we are same in R2, right? So we'll just go through these questions one by one. So the first case is the set A where the first component is non-negative. So I'm allowed to be anywhere in this place. Can be anywhere in this place. So is A a half space?
Yeah, this is half space.
Okay. What about B? So let's just so what will be B here? I have the second component as being non-negative, so this is going to be my B, right? And earlier we saw that A is something like this. This is my A. So what can I say about A intersection B?
It's a quadrant, right?
Yeah. So is it a polyhedron?
No.
Why not? It's an intersection of
Oh,
two half spaces,
it's
right?
polyhedron. Sorry. Yeah, it's a polyhedron. I was thinking polytope.
Polytope. Okay, yeah. So we are asking only about polyhedron. Yeah, correct. You are right. It's unbounded, but it is still a polyhedron, right? So A intersection B, polyhedron. Okay. What is the next question? Let me remove this. They don't have a eraser size change. Okay.
This is tedious.
Yeah, I think I'll have to switch to some other app. Not liking this Jamboard.
Yeah. Do you are working on an iPad or something? Means.
Yeah, I have, but I'm a bit worried about recording on the iPad. So I'm right now recording from my laptop.
Yeah, because iPad is much more convenient for annotating and doing things like this.
Yeah, maybe I'll just try this from next time. So till
Yeah,
now
it's
I've been
much
sticking
better
to
if
this.
you try iPad. Much better.
Okay. Yeah, I'll just try setting it up before next week. Yeah, also I think there's no copy tool. There's very little limited functionality in this one.
Yeah, its Jamboard is very limited.
So okay, all right. So here, as I was saying before, this is our A. This is our A, and C is given to us, which is saying the first component is less than equal to 1. So let's say this is 1 comma 0, and let's put this. All we are saying is this is C. So what can we say about A intersection C? So it is a polyhedron, yes? At least that part is fine.
Yeah, but it's not a polytope as before.
Uh, Correct. Because it's a wait, is it a polytope or not?
No, it's not a polytope, right? It's vertically, it's unbounded, right?
Yeah, yeah, exactly. So this is no, it's not a polytope because, like you said, it's unbounded. This slice keeps getting extended to minus and plus infinity. Right. So last question of this particular assignment before we move on to uh, some linear algebra revision. So the question is saying take intersection of all of these. Is that a polytope or not? So maybe I'll just, since there is no copy option, let me quickly write it down here and delete this. Okay, so what can we do here? Unfortunately, there are very few colors also. So have x, sorry, not x. A is this. Say first component greater than equal to 0. We have b as y greater than equal to 0. Okay, and okay, c is somewhere here. Oh, actually I made a mistake.
This problem is all about drawing stuff and nothing else.
Yeah, this part, but in general, so the thing is, I am drawing it, but actually you should write it. I'm just taking the easy route. So let's say if you are asked to prove, you can't just draw this and say this is the proof.
Yeah, anyways, in higher dimension, it will be difficult, right, to get a pictorial representation.
Yeah, so I mean, what I'm saying is even here, although pictorially it's simple, you need to write this down using the formulas. I mean, not the formulas. I'm saying the basic definition. You need to just verify those things.
You have to solve analytically, right?
Yeah,
That's what you are
yeah,
saying.
that's what I'm saying. Yeah. So if I have C here and then y less than equal to 1. Okay, I've run out of colors now. So
Yeah,
C.
the polytope, that everything.
So if I have intersection of everything, then where will I be?
Yeah, it's the square in between, in the middle.
This one, right?
Yeah, yeah.
Yeah. So basically, the answer here is yes. Okay. So any questions in this week's problems? Otherwise, I would like to solve some basic questions about eigenvectors and uh, some Taylor series related small derivations. I know I don't have much time, but whatever I can, I'll do today, and next time I'll continue with the revisions. I do want to cover a few things because I think one thing that is missing in the lectures is that a lot of these linear algebra basics they are not revised, so it will be helpful for you people, especially when you're solving questions from other reference books like Chong and Zach and Nosidal and other reference books. Also, would you like me to solve some questions about these convex analysis from Boyd, from the book Boyd?
Absolutely. It will.
Okay, so let me make a note of that. So,
Actually, I am reading the Chong book, Chong and Zach. I find it very readable book, but it's
yeah,
missing some of the proofs. The proofs they are referring to some other places.
right. Okay, so things to be done. you are saying that Boyd convex analysis problem set, right? Some
Yeah, some
problems.
representative problems that should suffice.
So about cones, hulls, what else is there? Polytopes, polyhedron. Okay, this is all right. Okay, so since I have about, how much time do I have? About 15 minutes, sure. So let me, mm, yeah, let me just talk about a few proofs which we typically know and not take it for granted, but let's just prove it for once. Eigenvectors of a matrix, let's call the matrix A, are linearly independent. How would I prove this? Any ideas?
Will the eigenvectors have the same values, or there is no restriction as such?
Uh, so what you are saying, I think I see what you are saying. I've not given anything like that. So I will just say that there is a matrix, there are a bunch of eigenvectors, and those eigenvectors are linearly independent. Not said anything about eigenvalues.
Yeah, maybe we can start from the definitions and see. Just start writing down Ax is equal to lambda x. Try to.
Okay, so let's say you have something like this. Okay, just two for example. No.
Suppose they are linearly independent and try to, let's see if I got a contradiction.
Uh,
Suppose they are linearly dependent.
suppose x equals to ky. Okay, so you have a ky is lambda 1 ky, ay equals to lambda 2y, so you have k times lambda 2y equals to k times lambda 1y. So you have lambda 1 equals to lambda 2. Okay, now,
So means if we can assume that lambda 1 is equal to not lambda 2, then
yeah, good point. Yeah, so yeah, I was expecting this. So yeah, this is indeed important. So if we are taking the eigenvalues to be the same, then like you see here, this is what happens. So we are assuming that the lambdas are different, but still it's not clear, right, how to prove it.
yeah, at least to me.
Yeah, this first step is definitely important, you are right. So it's a good start. So what since we are a bit short on time, let's just see what are the steps of the proof, and let me know if you have any questions. So we'll go by induction. What we'll do is we'll take n equals to 0. So here note that I said eigenvectors of a matrix, so I'm assuming it's a square matrix. So let's say it's an n cross n matrix. So let's take n equals to 1. It's a non-zero matrix. I said it's a non-zero matrix, so n equals to 1, so that means trivially true.
So it's induction in the dimensions of the matrix, right?
Yeah. Well, it's like okay, maybe let me, how do I put it? Is the induction on the eigenvector numbers rather. So n equals to 1 here, I mean that case coincides with the fact that the matrix. Do I want to put m here or not? Let's see. So okay, let me rewrite this. So that there is no confusion. So what I meant was, by induction on the number of eigenvectors. So if I take one eigenvector, let's say this matrix, some matrix m cross m, so sorry for the mixing up of m and n. So let's say if I have only one eigenvector for this matrix that I'm taking, will it be linearly independent? But I mean, it's a vacuous statement, right? It's just one. You
Yeah,
can't
it's
compare.
trivially true.
Yeah, so this is true, right? Because non-zero eigenvector E vector, this implies it's Li. It's just vacuously true. Now let's say n equals to k is true. This is our induction hypothesis. Okay. So what we are given is, we are given v1 to vn. They are all, oh sorry, yeah, v1 to vk rather. They are all linearly independent. Let's just assume that linearly independent eigenvectors of A. So now we'll take n equals to k plus 1. This is the induction step, right? So what we are given is v1, vk, and vk plus 1. Say that they are not linearly independent. And collect all the eigenvectors as columns of a matrix and call it M. Okay, v1 to vk to v1, v2 up to vk plus 1. So because I said that they are not, these k plus 1 are not linearly independent, and I'm assuming the induction hypothesis that the k are v1 to vk are linearly independent, so the rank of M is k.
K, right? K.
Okay. So far I just assumed something, so assume the induction hypothesis and just wrote what is the induction step. Now this what can the rank be at the most? K plus 1, right? But here I've said that the rank is k. So this implies, by rank nullity theorem, the dimensionality of the null space is 1, right? So there is a y, there is a unique y there's a unique y such that my is 0. Is that fine?
Yeah.
So remember that we are talking about A. M is nothing but all the eigenvectors of this matrix A. This matrix A just stacked here. Okay. So we want to use the property that these VI's are the eigenvectors of A. So let's do the obvious, which is multiply A here on the left side. So what we will end up getting is AMY is 0, our right hand side is 0 vector, so that doesn't matter. So what is this equivalent to? Saying A times this matrix M, which is V1, VK plus 1, Y is 0, is the same as saying V1, VK plus 1. Okay, running out of space. So what I'm trying to say is I know that A times Vi is lambda I times Vi. So I'm going to use that property of the I'm going to use the fact that AVIs are the eigenvectors. So what you will end up getting is v1 vk plus 1 lambda 1 lambda k plus 1 just a diagonal matrix. Y is 0. So notice that this is M. I defined M to be this exact matrix. So I am saying that, so what I am saying here is My is 0 and Mz is 0. But I said that, but dimension, and by the way z not equal to some scalar of y. But I said that the dimension of null space of M is 1, not 2. So this is a contradiction. So this implies eigenvectors of A are linearly independent. Does that make sense?
Yeah, these are very nice proof.
It's clear, right? I mean, what we are trying to do.
Yeah,
The
it's clear.
idea. Yeah. So we just maybe there are other ways of doing it. I just know this one way of doing it. So we have about 2 minutes. I can maybe quickly cover one more fact and then we can end it here. Otherwise, we can stop here itself. That's also fine.
I think we can stop here. Next we'll pick up.
Okay, sure. Yeah, next week maybe what I'll do is I'll just quickly go through this revision part first. I thought I could cover both, but I couldn't. And then I have a bunch of questions which are going to look long in terms of calculations, but I think it will be a good practice for you people to apply these first order and second order necessary conditions to determine candidate stationary points. Okay. So it will also be somewhat of a good practice in terms of vector calculus. So we'll see how that goes. And I think one point that you brought is that it will be nice if I can add some questions about convex analysis from Boyd's book, some representative problems. Okay, let's see how much we can try, how much we can fit in the next one. But yeah, I don't want to skip this revision part. I think that's very important. There's one, for example, just to give a teaser. I'll stop here. Just give me a minute. So just what I'm trying to say is, I have a function that is multivariate. So often you will soon see that this x and this yeah, okay, I mean, okay, there's some high dimensional space in which you're optimizing, so that's your x, it's some Rn space. And often when you're optimizing, what you're doing is you are looking at some direction D, some set of feasible directions D. You are taking a step along the direction D, from x. Okay, alpha is just a scaling
also
factor.
in Rn. So excuse me, D is also in Rn, right?
Yeah, correct, yes.
Oh.
So the point that I'm trying to make is here, if in general, if I want to look at the gradient of this function, the gradient is going to also be in Rn, right? But if you know, it's always difficult to compute this expression. So instead, what we do is, what I have written here, I define that itself as a function. It's called a line trace of a multivariate function. Anyway, I'm not completing it right now. I'll do it next time. But what we do is we call this function f of x plus alpha d. So you fix x, you fix a direction. Along that direction, you can go. You pick a point. Let's say you are here. Pick a direction. Now here you can go along this line, so to speak, in that Rn space. Call that as my function g alpha, and what I can end up showing is things like g dash alpha is d transpose gradient of this f of x plus alpha d. And whenever I get these complicated Taylor series expansions, Taylor series expressions, I can use these quantities which are just one dimensional functions. It's easier for me to manipulate or compute things corresponding to this 1D function. So we'll see how to equivalently boil down these multivariate functions in terms of these simpler or scalar valued 1D functions. Okay. So I thought that it would be nice if we can see some examples of these things.
What is this called? Line trace.
Line trace of a multivariate function. So this maybe I'll just solve some examples to perhaps make us see the point. Especially when we'll start doing some constraint optimization problems, you will see that if I use these g alpha functions, it becomes a bit easier for me to state my problem a bit compactly and just solve analytically. Okay, so let's just give me a moment. Let me stop the recording.